Hello, in today's lecture, we are going to study something about regular points. So what are regular points? See, a point, very simply I'm writing at first, a point Z naught is called as a regular point, is called as the regular point of function fz if fz is analytic at the point z equals to z naught. So this particular point z naught is called as a regular point. Now, let us pay a little bit of attention that we have already done also. So we've seen that if function is differentiable at a point, if a function is merely differentiable at a point, uh, does it qualify for the definition for analyticity? The answer is no. Okay. So if function is analytic at a point, function is differentiable at a point z naught, it simply means that it's different. The derivative exists at z naught. But when we are talking of analyticity, there should exist some neighborhood about z naught where function must be differentiable. So when we are talking of analyticity, we are talking of some neighborhood where the function should be differentiable. Okay. Now this brings us to an important discussion of defining it all the more. Okay. So when I've said that it should be analytic, it implies what? So let's say my function is defined from D to C, and z naught be some point belongs to D. So z naught is a point, and let's say it is a regular point. Let us assume that z naught is a regular point. If I'm saying it is a regular point, it implies what? It implies that there must exist. Regular point means what? Z naught function is analytic at point z naught, and if function is analytic at point z naught, then there must exist some neighborhood about z naught where function must be differentiable. That implies there exists some del greater than 0 such that function is differentiable on the open disk centered at z naught with radius del, or there must exist some del greater than 0 such that f dash z exists for all z belongs to open disk centered at z naught and of radius del. Or if you want to write a little bit simply, there exists some del greater than 0 such that f dash z exists for all z belongs to z minus z naught modulus less than 10, whichever way suits you. Okay, so this is point z naught. So z naught is called as regular point if function is analytic at that point. It implies that function must be differentiable in some neighborhood containing that point z naught. Okay, so now let us go a little bit further and let us try to understand what other things can be or what other meaningful things can be derived from this. So let us say I'm talking of an open disk. Okay, let's say I'm talking of an open disk. Just give it a minute. Let's say I'm talking of an open disk. So this is an open disk. Okay. So I'm not including the boundary, but I'm including the inside of it, interior of it. It implies what? It simply implies that if f is regular, so I'm saying if f is regular at some point z naught, then clearly there should exist some del greater than 0 such that f dash x exist in some neighborhood of z naught. Okay. So let us take some point here. Let us say I'm taking a point zeta here. Okay, let us take a point zeta here. What does it imply? This particular point zeta obviously lies inside this interior of this particular zeta lies inside of it. So basically zeta is what? Zeta is an interior point. Okay, zeta is an interior point, any arbitrary interior point. Okay, just pick any arbitrary interior point. Okay, now this zeta is what? This zeta is obviously lying inside this particular open ball of radius del. This is clear. Okay, and this is open set. I'm writing this isn't. Clearly it is an open set. Okay, so what will happen? Since it is an open set and zeta is interior point, so zeta is interior point means what? There must be some neighborhood containing this point zeta and which must be contained in this set S. So let's say if this is my set S and this is my set S, which is like B Z naught comma del is, let's say, set S, then there must be some neighborhood of this zeta which must be contained in S. So by the definition of interior point or open sets, open set, there must exist some, let's say, del dash such that z minus zeta modulus must be less than del dash, and this particular open ball that is centered at zeta and radius del dash, it must be contained in what? It must be contained in open ball centered at z naught and del. Okay, it is clear, I hope. It implies what? It implies that function is differentiable at zeta also, and function is differentiable at zeta, and f dash z, since it exists for all this thing, so it exists here also. So it implies what? It implies that function is differentiable in some neighborhood of zeta also. It implies what? It clearly implies that zeta is also a regular point. It implies that zeta is also a regular point. If zeta is a regular point, how many points are there in this particular open set? So because it is an open set, so I will say that there are uncountably many. Contains how many points? It contains uncountably many regular points. Did you get my point? What I wanted to convey? See, if I'm saying a point is regular, it implies that there must exist some neighborhood where the function is differentiable. In this entire neighborhood, I mean this entire disk, at all points function is differentiable. Now what I've taken, I've just taken a point zeta. Zeta is an interior point. It implies that there must exist some neighborhood containing the zeta, which must be contained in this particular set. That is the open ball centered at z naught comma del. It implies what? Function is differentiable at zeta and also in some neighborhood containing the zeta. It implies zeta is a regular point. And so it implies that each point which is contained in this open disk, at each point is the point of analyticity. If each is the point of analyticity, if each of these points are points of analyticity, so the question arises, how many points are these? So these are uncountably many regular points. So always remember, this is an important point that I'm going to write, that if I'm claiming that function is regular at a point, so I'll just write if f is regular at z naught, it implies that f must be differentiable at uncountable number of points. At uncountable number of points. I hope this is clear. Okay, it is clear. Okay, because interior of a set will contain always uncountably many points. I mean, this is evident. I mean, this you can do on your own also. So f must be differentiable at uncountable number of points. Point number one. Okay. What does it imply? Further, if f is differentiable, if f is differentiable only at most countable number of points, countable number of points, then always remember f cannot have regular point. Because for f to have regular point, f must be differentiable at uncountable number of points. If I am saying that f is just differentiable at countable number of points, then it implies f cannot have regular points. I hope this is clear. Now let us extend this thing to analyticity. See, I've already told that if function is having a regular point at z naught, then function must be analytic at z naught. Okay. So it implies what? It implies that if f is analytic at a point, if f is, because f is analytic at what? Regular points only. So if f is analytic at some point z naught belongs to D, it implies what? It implies f must be differentiable in some open neighborhood containing this point z naught. It implies that f must be differentiable at uncountable number of points. F must be differentiable at uncountable number of points. Okay, so if f is analytic at z naught, then f must be differentiable at uncountable number of points. And reverse, if I want to write, if f is differentiable only at most, you can say only at countable number of points, countable number of points at most, then f is nowhere analytic. F is nowhere analytic. So these are some important points that I want to mention in this particular lecture. Okay. However, remember this thing also, that here I'm writing that if f is differentiable at uncountable number of points, uncountable number of points, it does not imply that f is analytic on some z naught. I mean, this is important point that you should really remember. Let us take an example and let us understand the final point that I mentioned right now. All other points I have derived. I'll just give you some a few points or questions to really understand all those things. Don't worry about it. So let us first take one example. Let us take an example of fz is equals to x square plus iota y square. Okay. Now clearly, the first order partial derivative exists and it is continuous. all the first order partial derivative exist and they are continuous, right? And Cauchy-Riemann conditions hold. Cauchy-Riemann conditions hold good only for x equal to y. So Cauchy-Riemann conditions hold good only for x equal to y. It implies what? It implies that f is differentiable. F is differentiable on line y is equal to x. It also implies that f is differentiable at uncountable number of points. Because on this line, there would be uncountable number of points. Because after all, x belongs to R. Okay. So f is differentiable on uncountable number of points. But does it imply that f is analytic? No, not at all. See, if I take at this particular point, function is differentiable, then function to be analytic, it must be differentiable in some neighborhood containing this point. But function is clearly not differentiable at any of these points, like any of these points in the neighborhood of this particular point. Here function is non-differentiable. So it implies what? It implies that function is nowhere analytic. Okay, so function is nowhere analytic, although you can clearly see that function is differentiable at uncountable number of points. So you have to remember the statement not this way. You have to remember that if function is analytic at a point, then it must be differentiable at uncountable number of points. But if function is differentiable at uncountable number of points, but it is not always necessary that function is analytic. Okay, here is an example where I have proven that if function is differentiable at uncountable number of points, we've seen that function is nowhere analytic. Okay, so you have to keep this in mind. Not just I'm giving you a few things to really consolidate your understanding, and I hope you'll be able to consolidate your understanding from these two. If I take fz is equal to cos z bar, sorry, sin z bar, is function fz analytic function? Is fz an analytic function? Let us see if that's the case or not. See, from the complex form of the from the complex form of Cauchy-Riemann conditions, we understand that if f is differentiable at point z naught, it should imply that del f upon del z bar must be 0 at that particular point. This is something that we have already done. So if f is differentiable at point z naught, then del f upon del z bar should be 0. It implies what? It implies that cos z bar at z equal to z naught must be equal to 0. It implies what? It implies that z naught must be equal to what? It should be equal to 2n plus 1 pi by 2. It implies that f is differentiable only at countable number of points. Only at countable number of points. So therefore, it clearly implies that f is not analytic. In fact, it's not analytic anywhere. Because I've already told you that if f is analytic, then f must be differentiable at uncountable number of points. I hope it is clear. Now let us take another example and appreciate this concept. Okay, so let us take another example. Let us take an example where I have written that I have already given this example also. Let us say Pz is one polynomial. Let's say Pz is a polynomial. And I'm replacing this z by z bar. So let's say this new polynomial Qz, which I have replaced with z by z bar. So this is it. Now question arises whether QZ is analytic or not, or if it is analytic, in which domain. Okay, this is what I'm asking. So if QZ is analytic, it implies what? Del Q upon, first let us find the point of differentiability. So del of del Z bar, if it is equal to, if Q is differentiable at certain points, then at those points del Q upon del Z bar must be 0 by Cauchy-Riemann conditions. It implies what? It implies A1 plus 2A1, sorry, A0 will go 0, 2A1 plus, so sorry, 2A1 plus, so sorry, yeah, A1 plus 2A2 Z bar plus 3A3 Z bar whole square dash 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 N A N Z bar raised to power N minus 1. This should be equal to what? 0. Okay. Now, what is the highest degree this polynomial has? N minus 1. And from fundamental theorem of algebra, we know that it can have N minus 1 roots only. It can have N minus 1 roots. It implies what? It implies that Q is differentiable. Q is differentiable only at, and this N belongs to natural, only at countable number of points. And in fact, finitely countable, because in order to define this thing, so it is like only at countably finite number of points, or rather I would say they are differentiable. Q is differentiable only at most finite number of points. So now, according to the discussion that we had today, it implies that QZ is nowhere analytic. QZ is nowhere analytic. Now let us just modify this question, and now let us take another question. I think these questions are like, you can get now what I wanted to suggest. So if, let's say I'm taking two polynomials PZ and QZ, they're polynomials in okay. And now let me define Fz equals to let's say Pz into 2Z bar. What I have done, I have simply changed this particular thing now. I have written that Fz is what? Pz into Qz bar. Now I want to know whether this function is analytic or not. Whether Fz is analytic or not. So let us first find at how many points this function is differentiable. So if function is differentiable, then it should satisfy this Cauchy-Riemann condition. So it will be differentiable at how many points? So this is a function of z. So with respect to z bar, I cannot differentiate. So it will give me what? It would simply give me Pz into del q z bar del z bar equal to 0. Now, you know, let's say if I say that Pz is a polynomial of, let's say, degree n. Let's say it is a polynomial of degree n, and let's say Qz bar is a polynomial of degree m. So what will happen? This will be of degree m minus 1, the derivative of Qz bar with respect to z bar, and this will be of degree n. So at most, this particular thing will have zeros at most n into m minus 1. At most n into n minus 1 zeros. In fact, you can not write at most, you can write that total number of zeros from this particular product can be n into m minus 1. Okay. So in fact, I would write that it can have finitely many points of differentiability. If it can have finitely many points of differentiability, what does it imply? It implies that f cannot be analytic. cannot be analytic. However, there is one possibility. There is one possibility in which it can be analytic. What is that possibility? If Q becomes a constant polynomial, if Q becomes a constant polynomial, then obviously this becomes zero irrespective of what, your like. So basically, F can be analytic at point Z naught if and only if QZ is a constant polynomial. Okay, because then for all Z, this particular thing would become zero. So then it can be analytic. Otherwise, it is not analytic because it is because if this is a non-constant polynomial, then it can have zeros only for some finitely many points. So it can be differentiable only at finitely number of points. If I'm saying that if QZ is simply what? Constant polynomial, then it is not a problem, because if QZ is a constant polynomial, then this particular thing would be zero for all Z belongs to C. That's not a problem at all. Or otherwise, you can say that if QZ is a constant polynomial, then constant into PZ is simply a polynomial, and polynomial is an analytic function. So it is an analytic function everywhere. So whichever way suits you, so it will be fine. So F can be analytic, then F can be analytic if QZ, if and only if Z not belongs to C, if and only if QZ is a constant polynomial. You can see now, if QZ is a constant polynomial, then this is completely a polynomial. A polynomial function in a complex polynomial function is always analytic. So that's not a problem. So I hope in this lecture you are able to get it. If my speed is more, or if I'm not able to convey any idea, kindly let me know in the comment section. Till then, take care. Bye-bye.